This will be a mildly theoretical video on the existence of Gaussian processes. Now, you might be saying, what do you mean, the existence of Gaussian processes? You just gave us two examples of Gaussian processes. So we know that Gaussian processes exist, and you would be right, that's true. But what the theorem on the existence of Gaussian processes says is not that there exists some Gaussian process, but that you can choose these finite dimensional distributions at will, and there will be a Gaussian process with those finite dimensional distributions. So we're going to state that result. And fortunately, it takes a very simple form for Gaussian processes as opposed to random processes in general. And here's the theorem. It uses some nice results by Kolmogorov. So for any set S, this is looking similar to the definition, for any mean function, I'll write it as mu from S to R, and any covariance function k from S cross S to R, there exists a Gaussian process zt on S such that the expected value of zt equals mu of t, and the covariance of zst equals kst, and this is for any s and t in S. And now I haven't defined what a covariance function is, but we will do that shortly. I'm going to give you a few examples first of more interesting Gaussian processes before we get to the rigorous definition of a covariance function. But it's a very simple thing. I could just say it right now. It's just, for any finite set of points that this function that gives you a positive semi-definite matrix, a symmetric positive semi-definite matrix. In other words, that this gives you a covariance matrix. But we'll get into that in more detail, and we'll see some nice properties of covariance matrices. So what is this theorem saying? What is, why is this a nice thing to have? Well, the beautiful thing about this is that it lets us construct Gaussian processes with prescribed mean and covariance. So we can just choose some mean function, pick your mean function, whatever you want, pick your covariance function, you can prescribe the pairwise covariances, and then you get a Gaussian process on S with those mean and covariance. So this is actually a very, very nice fact. And when I say construct, I mean mathematically speaking, you can construct it. I mean, of course, you can never actually physically, computationally, because like if S is R, like for this example, you're always going to be dealing with only a finite set of values in S whenever you're doing something in practice. So really, maybe I should say that this is not actually relevant for practical applications. I mean, because like I was just saying, in any practical application, you're always looking at only finitely many points of S. And so you're always in this situation. You're always in the trivial situation where you just have some multivariate Gaussian on finitely many, it's indexed by finitely many things. So it's just a multivariate Gaussian. So in practice, you're always in the trivial case, which is sort of an interesting thing. And so in fact, this more general statement, the fact that there exist these more general things, is really only really important for theory. It's only really important for when you're trying to prove things about these more general objects. Okay, so that's just a very brief description and statement of the theorem on the existence of Gaussian processes, and we will use this in the next couple videos to write down some covariance functions, and then we can just generate a bunch of Gaussian processes, and we'll see what we get. So that's going to be fun. Oh, and one more thing maybe I should mention here is that it's enough to specify the pairwise covariances, because then for any finite number of indices, t1 through tn here, by specifying the pairwise covariances, we have specified the covariance matrix, and we have also, of course, specified the means by the mean function, and that the mean and covariance matrix defines a multivariate Gaussian distribution on those points. So it's enough to just define these pairwise. We don't have to define the distribution on every finite subset. That's actually a special property of Gaussian processes as opposed to random processes in general. Okay, so that's existence of Gaussian processes.